do was, if we knew that two scores were drawn from normal distributions, to think about how we might compare them. So we use the example of the SAT and the ACT exams. Here I've kind of just made up a little bit of simplification. We are saying that the SAT exam is normally distributed with a mean of 1800 and a standard deviation of 300, and the ACT will be normally distributed with a mean of 27 and a standard deviation of 5. So we'll just create, again, some samples of 10,000 drawn from these normal distributions, 1800 and 300 and 27 and 5, and create a data frame of those. And you see that we have our scores. And here we can plot those distributions side by side. Now I can't put them on the same plot because the x coordinates for where the SAT is centered are much larger than where that of the ACT are centered, right? This is at about 1800, where this is at about 27. So they would be very far apart. We can't really compare these as is right now. So the question is suppose that we have a score from each of these tests, a 30 and a 2000. So you know your 2000 is right here, and your 30 would be out here. And the question is which one is better? Is 2000 better on the SAT than a 30 on the ACT? And how can we figure that out? So the idea that we discussed was exactly what we had just started looking at, was framing these things in terms of standard deviations. So we'll say how many standard deviations away from the mean is 2000 and how many standard deviations away from the mean is 30, and whichever one is more would be a higher score. So recall how we did that. We took our point, and I'll write it as x sub I now, minus the mean, and we divided by the standard deviation. So let's determine the score for each of these points, the 30 and the 2000. So for the 30, we would say the 30 minus 27, the mean, over 5, the standard deviation. Okay, so that means 30 is 0.6 standard deviations away from the mean of the ACT data. And for the SAT, we'd say 2000 minus 1800 divided by 300. And we get 0.67. So it seems that the SAT is a little bit better than the ACT score here because it's a more standard deviations away from the mean. It's further to the right of the mean than is the other data point. Okay, and we can also convert scores here. So if we wanted to compare, like, what would an SAT score of 2200 be in ACT, or be on the ACT, right? What's the equivalent? Well, we just say how many standard deviations away from the mean is 2200. So 2200 minus 1800 divided by 300 is 1.3. And we just have to go to the ACT and say how many, what is the point that's 1.33 standard deviations away from the mean. So the mean was 27. We would add 1 point, just use this as an approximation here, times the standard deviation, and it seems that it would be a 33.6 is the equivalent score on the ACT to a score of 2200 on the SAT. All right, and this is really kind of where we want to be. And further, if we take and subtract the mean and divide by the standard deviation of each of these points, we'll actually be able to plot them together. So let's go ahead and do that. So if I take and instead I let this data be the SAT minus 1800 divided by 300, and the ACT, I'll take all those scores and subtract 27 and divide by 5. Now, if we look at our data, you see that they scores look like they're similar, and we can actually plot them both together. Make the first one be SAT, and make the second one the ACT. And you see that we have two plots that are very similar on top of one another. But that's because what we did was normalize these scores. All right, we put them both in terms of standard deviations instead of the actual value. And now we can compare those distributions. And in this case, it looks like they're almost the same. Right? It doesn't look like performance is very different on the SAT or the ACT. Okay, but again, that's the big idea of z-scores, is turning everything into standard deviations instead of absolute values.